Okay, students. Now we'll speak about the force acting over a charged particle which is moving in an external magnetic field. The topic that we are going to speak now is force acting over a charged particle which is moving in an external magnetic field. That is, let us have a charged particle, let's say plus Q, which is moving with an initial velocity v in this direction. A charge plus q is moving with an initial velocity v in this particular direction. Then we are asked to find out the force. For that, this charge particle, it is kept in an external magnetic field which is like this. The charge particle is moving in an external magnetic field which is in this direction, that is in the red line. Okay, the magnetic field intensity and the velocity, it is having an angle theta. Then it was experimentally found that the force acting over this charge particle is directly proportional to charge, velocity with which it is moving, the external magnetic field intensity, and sine of the angle. The force was directly proportional to QVB sine theta. It was experimentally found. Then we could write F is equal to a constant into QVB sine theta. This proportionality constant that we are multiplying over here, it is K, that is equal to 1. Therefore, in this case, we could write F is equal to QVB sine theta. This is the force acting over a charged particle which is moving in an external magnetic field. If we are trying to move a charged particle in an external magnetic field, it will experience a force of F is equal to QVB sine theta, where Q is the charge, V is the initial velocity, B, it is the magnetic field intensity, that is the external magnetic field intensity, theta is the angle between external magnetic field intensity and velocity. Then we could write two special cases. If theta is equal to 0 degree, that is magnetic field is parallel to velocity. Let me write magnetic field is parallel to velocity. Then sine 0 value will be 0. As a result of that, we could write F is equal to what? We could write F is equal to QVB into 0, that is 0. Therefore, force is minimum, or the force will become 0 at an angle of 0 degree. If the charged particle is moving in a parallel magnetic field, the force will be 0. The force due to magnetic field will be 0. And the next special case is if the angle is 90 degree, that is magnetic field is perpendicular to velocity, then sine 90 value, it will be, it's not 0, it's 1. Sine 90 is 1, means force will become QVB into 1, that is QVB, that is maximum. The force is maximum at an angle of 90 degree and the force is minimum at an angle of 0 degree. This is the force acting over a charged particle which is moving in an external magnetic field. This force is otherwise called as magnetic Lorentz force. This force, which is due to the external magnetic field, it is called as magnetic Lorentz force. Okay, remember this. There's another way of representing this magnetic Lorentz force, that is F is equal to Q into V cross B. VB sine theta, it can be written as V cross B, and the force is having another way of representing, that is F is equal to Q into V cross B, where FV and B, they are vector quantities. The force will be in the direction of V cross B. Therefore, this is called as magnetic Lorentz force. Now we know what's magnetic Lorentz force. Then let us understand what is electric Lorentz force. Electric Lorentz force, for understanding electric Lorentz force, we have studied E is equal to F by Q. the relation between electric field intensity and electrostatic force, it is E is equal to F by Q. And we have learned this equation. Therefore, we could write F is equal to QE. What is this F? This is the force acting over a charged particle which is in an external electric field. This was the force acting over a charged particle which is placed in an external electric field. Therefore, this force is called as electric Lorentz force. What is this force called? This force is called as electric Lorentz force. Let me write electric Lorentz force as F suffix E. What is electric Lorentz force? It is the force acting over a charged particle which is in an external electric field. What is magnetic Lorentz force? Magnetic Lorentz force is the force acting over a charged particle which is moving in an external magnetic field. Moving in an external magnetic field. Let me call this SFB. Magnetic Lorentz force is called as FB, and electric Lorentz force is called as FE. Then let's have another situation where if the charged particle is moving in a combined magnetic field or combined electric and magnetic field, let us assume that the charged particle is moving in a combined electric and magnetic field, then the total force acting over that charged particle will be the vector sum of electric Lorentz force and magnetic Lorentz force. If the charged particle is moving in a combined electric and magnetic field, the total Lorentz force acting over that charged particle, it will be the vector sum of electric Lorentz force and magnetic Lorentz force. As we know, the electric Lorentz force Fe is QE and the magnetic Lorentz force is Q into V cross B. I could write this expression as Fe is equal to QE plus Q into V cross B, where electric field intensity is vector, velocity, magnetic field intensity is also vector. Therefore, total Lorentz force is like this, from which we could take that Q common out, then it will become E plus V cross B. Okay, this is the expression for total Lorentz force, where E, V, B, they are vector quantities. Okay. Therefore, this is the total Lorentz force acting over a charged particle which is in a combined electric and magnetic field. Okay, total Lorentz force. Now we know what is magnetic Lorentz force, what is electric Lorentz force, and what is total Lorentz force. Then let us understand the direction of magnetic field intensity. In order to find out the direction of magnetic field intensity, we will be using a rule which is called as Fleming's left hand rule. For applying that Fleming's left hand rule, let me create a situation over here. That is, we are having a place where the magnetic field intensity is inverse. There is a uniform magnetic field which is inwards to the screen like this. Then in that uniform magnetic field, if we are trying to move a positive charge particle with a velocity v in this direction, what is the direction of force acting over that charge particle? What is the direction of force acting over that charge particle? That is obtained by our Fleming's left hand rule. Fleming's left hand rule. Let me make you understand what is Fleming's left hand rule. I am having my left hand. This is the forefinger of my left hand. This is the middle finger of my left hand. This is the thumb. I could place my forefinger, middle finger, and thumb in the mutually perpendicular direction. That is, if my thumb is in the x-axis, then my forefinger will be in the y-axis and the middle finger will be in the z-axis. You can see my hand. Then you have to place your left hand in such a way so that the forefinger denotes the direction of magnetic field. Forefinger, it denotes the direction of magnetic field. Middle finger denotes the direction of current. Middle finger denotes the direction of current. Then thumb will represent the direction of force. Hold your left hand in this way such that forefinger will represent the direction of magnetic field, middle finger will represent the direction of current, then thumb will represent the direction of force. Let's try to place our left hand in that manner. For which, what's the direction of magnetic field over here? The direction of magnetic field is inwards. You could see the direction of magnetic field in this screen is inwards. What is the direction of current? The direction of current, for that we have to go to our current electricity chapter. Current is in the direction of flow of positive charge. Current is in the direction of flow of positive charge. Therefore, in our situation, the positive charge particle is moving in one direction. If the positive charge particle is moving in one direction, then we could place our forefinger in the direction of field. Let me place my forefinger in the direction of field, that is field is inwards. I should place my middle finger in the direction of current. Middle finger in the direction of current means you should hold your left hand. Don't just look at my left hand. You should hold your left hand such that forefinger denotes the direction of field. Then middle finger denotes the direction of current. Then thumb will denote the direction of force. According to my left hand, I am getting the direction of force upwards. Are you also getting the direction of force upwards? Take your right hand, place the forefinger in the direction of field, place the middle finger in the direction of current. That means if the positive charge is moving in this direction, means the current is also in the same direction. Therefore, middle finger is placed in the direction of current, then thumb will represent the direction of force. Okay. Therefore, this is how we are getting the force by Fleming's left hand rule. Okay. Now we have understood what is Fleming's left hand rule, and we have understood how the direction of force is. Okay. Therefore, the direction of force is upwards. Okay. Then we are having a positive charge which is initially moving towards the direction that is marked in red color, but it is experiencing a force upwards. As a result of that, the charge particle will deflect upwards in this direction. It will deflect upwards in this direction, and if the charge particle is deflecting upwards in this direction, after some time the charge particles will have a position over here. Then at this instant, at this particular instant, the charge particle will experience an instantaneous velocity which is tangential to the motion. That is, at this particular instant, the charge particle's velocity will be in this direction. If the charge particle's velocity is in this direction, then we could use our Fleming's left hand rule, so that the forefinger denotes the direction of field, middle finger denotes the direction of current, then thumb will represent the direction of force. That means we will get the direction of force in this direction. Therefore, you could use your left hand so that you could understand the force at this instant is in this direction. As a result of that, the charge particle will get deflected again and it will reach a point somewhere over here. Therefore, let me draw the new position of charge particle over here. Then it will experience an instantaneous velocity in this direction, that is tangentially to that green curve. Then if you are using your left hand to find out the direction of force, that force will be in this direction. You could verify it with your left hand. Okay. Then the charge particle will again deflect and it will reach somewhere over here. Then let me mark the position of positive charge particle at that instant over here. Then the velocity will be downwards, and if you are using your left hand to find out the direction of force, you could get the force direction is like this. As a result of that, the charge particle will move like this. Then you could understand the motion of charge particle, it will be circular. Can you see it? Therefore, if a charge particle is moving in a perpendicular magnetic field, If a charged particle is moving in a perpendicular magnetic field, you just refer the direction of magnetic field. It was inverse. The direction of velocity is perpendicular to the direction of magnetic field. Therefore, if a charged particle is moving in a perpendicular magnetic field, it will rotate. If a charged particle is moving in a perpendicular magnetic field, it will rotate. Okay, did you understand this? The important thing is the charged particle which is moving in a perpendicular magnetic field, it will rotate. Okay, therefore, if it is rotating, what force is causing it to rotate? The necessary centripetal force required for this rotation is provided by the magnetic Lorentz force. That is, we have learned in our +2 that every particle, in order to execute a circular motion, there should be a force which is directed towards the center. That force is called as centripetal force, and in this case the force which is directed towards the center is provided by which force? Magnetic Lorentz force. In this case, it's clear that the magnetic Lorentz force is providing the necessary centripetal force. You could see this force which is directed inwards or towards center is provided by the magnetic Lorentz force. As we know from our +1 syllabus, the expression for centripetal force is mv square by r. What's m? M is the mass of the charged particle, v is the instantaneous velocity, r is the radius of the circular path. Therefore, centripetal force can be replaced as mv square by r. What is FB? FB is magnetic Lorentz force. FB is magnetic Lorentz force. Therefore, magnetic Lorentz force can be replaced as QVB sine theta. Can you say what's theta in this diagram? Theta is the angle between velocity and field. In this diagram, it is clear that velocity is perpendicular to field. Since V is perpendicular to the external magnetic field, we could write, therefore, theta is equal to 90 degree. Hence, we could write this expression as mv square by r is equal to qvb. Can we? Yes, we could write mv square by r is equal to qvb. Okay, then we could cancel one v square and v. Then we will get v is equal to qb r by m. This is the expression for instantaneous velocity. The expression for instantaneous velocity will be v is equal to qbr by m. Okay, then let's find out the expression for radius. If you're taking this radius to other side and if you're aggregating all the terms to the next side, you will get r is equal to what? R is equal to mv by qb. R is equal to mv by qb. Okay, therefore this is the expression for radius of the circular path. Radius of the circular path. From this expression, it is important that you should notice one interesting relation, that is radius, and over here it is velocity. In this case, mass of the charged particle is a constant. It won't change if it is rotating. The charge of the charged particle will also be a constant, and the external magnetic field that is given, it's also a constant. Therefore, in this case, it's clear that radius is directly proportional to velocity. Radius is directly proportional to velocity means you should understand, if the velocity of the particle is increasing, the radius will also increase. Or if the radius of the particle is increasing, the velocity will also increase. The radius is directly proportional to velocity. Remember this also. Then let's find out the kinetic energy. If we have to find out the kinetic energy, what's the expression for kinetic energy? The expression for kinetic energy is half mv square. We have learned it in our +1, half mv square. What's v? As we know, v is qbr by m. We could substitute the value of velocity over here and we'll get half m into v square, means it is q square b square r square divided by m square. We are substituting for v and we are getting an equation like this. Then we could cancel this m and m square. We'll get ultimately q square b square r square divided by 2m. What's the expression for kinetic energy? It is q square b square r square divided by 2m. This is the expression for kinetic energy attained by the rotating charge particle. Then let us find out the expression for time period. What is time period? Time taken for one complete revolution. The time taken for one complete revolution, it is called as time period. What is time period? In this case, it is the time taken for one complete revolution. And for saying the expression for time period, let's recall, we know omega. Omega is angular velocity. We have learned omega as 2 pi by t. This is an expression for omega which is having a connection with time period, that is omega is equal to 2 pi by t. And we have learned omega is equal to v by r. Since we have an expression v is equal to r omega, we could write omega equal to v by r. Omega equal to 2 pi by t and omega equal to v by r. It is the two expressions that we have learned in our +1 for angular velocity. Then we could write 2 pi by t is equal to v by r. Then we could ultimately write t is equal to 2 pi r by v. We could write t is equal to 2 pi r by v. Then from this relation, can you say what is r by v? In this relation, if you are finding out r by v, it will become m by qb. R by v will be m by qb. Therefore, we could write time period as 2 pi, r by v can be replaced as m by qb. Therefore, the expression for time period of the circular motion in this case will be t is equal to 2 pi m by qb. Time period is t is equal to 2 pi m by qb. Okay, the expression for time period. Okay, now we know the expression for time period of the circular motion. Then let's find out the expression for frequency. For that, what's frequency? Frequency is the number of revolutions completed in 1 second. Frequency, it is the number of revolutions completed in 1 second. What's the relation between frequency and time period? It is frequency is the reciprocal of time period. Therefore, in order to get the expression for frequency, you just have to take the reciprocal of time period, that is 2 pi will become 1 by 2 pi, m by qb will be becoming qb by m. Therefore, this is the mathematical expression for frequency of the circular motion. Now, so far, what did we learn? We have learned that a charge particle which is moving in a perpendicular magnetic field, it will execute a rotational motion. And if it is executing a rotational motion, the instantaneous velocity that it will have will be qbr by m. The radius of the circular path will be mv by qb. The kinetic energy obtained by the charge particle will be q square b square r square divided by 2m. The time period of revolution will be t is equal to 2 pi m by qb, and ultimately frequency will be 1 by 2 pi into qb by m. Okay, therefore we are getting an expression like this. We could remember this as qb by 2 pi m. Okay, this is our expressions. We will stop our current video over here.